So Martin, Bridson will start and talk about the geometry of the conjugacy problem for finitely presented groups.
Thank you, Catherine. It's a pleasure to be back here in Bonn. I was here, I think. I don't remember what I talked about. So I'm going to talk about the conjugacy problem. I must say, I feel slightly fraudulent. It's so nominally, of course, decision problems are logic and group theory, but there's no logic methodology in what I'm going to say today. I have been thinking about first order logic recently, so I'm looking forward to talking to people and listening to the other talks. So a lot of what I say, not everything, but a lot of it's with Tim Riley and Cornell. And a couple of other names will come up as well. And this is stuff that I know when I started this, because I started thinking about this during COVID. I spent a lot of time thinking about this during COVID. And I half wrote lots of notes. And then I didn't finish those papers for various reasons, partly because I couldn't prove all the theorems I wanted to prove. And then I had a sabbatical this spring, which was wonderful. I went to Stanford for 3 months, and I was just alone in my office writing. So there's a whole bunch of papers. It says my notes, there's 5 papers so far. There should be another 4 before Christmas explaining all of this. So when I came to prepare this talk, it was the first time I really talked about it properly. I was trying to say too much, so I'm not going to say it all. I'll try not to rush, but I'll try to give you some overview of what I'm trying to do and describe some of the highlights, and it's sort of an invitation, because I think there's a lot of interesting open problems here. So of course there's nothing, so first, in case I forget, let me have a finally presented group. So I'm going to try, you might wonder why I stick to finally presented groups in this talk. It's really because that's what I believe in. They're the hard ones. Somehow finally generated groups are too easy. You can encode too much stuff into them. The real stuff is finally presented groups. And so I'm interested in the conjugacy problem for finally presented groups. Okay, so given what? I'm always unsure whether to take elements or words here. But let's say given with the conjugacy problem, as you all know, give let's say 2 words in the free group. On the A's, maybe I'll abbreviate that to just A later. Does there exist some W so that W conjugates U to V in the group? Okay, that's actually the conjugacy problem. Now, I want to think about it geometrically. So. This might get a bit hidden, but I'll usually think of this as the fundamental group of some nice space. Now, sometimes that'll just be the standard 2 complex of the presentation, right? So, we take one vertex and take a 1 cell for each generator, and then stick on the relations. Then 2 complex for the right fundamental group, but then you can always embed that in R5, for example, take the boundary of a regular neighborhood and make that into a smooth 4 manifold. So you can take your favorite finally presented group and you can always make it the fundamental group for a closed 4 manifold if you want. Smooth. And that's convenient now, because what I'm about to say will work for any nice space, but it makes best sense for a manifold. So if you want to study the geometry the conjugacy problem. I think of this as having 2 main aspects. So first of all, as you all know, so conjugacy classes in your group, if your group is now the fundamental group of something, so that corresponds to, what's it correspond to? It corresponds to free homotopy classes of loops. In your manifold. Well, you don't need to talk about a base point during conjugacy, you don't like the word problem. Okay? And this is really a very nice correspondence. And so I'm not really going to do Riemannian geometry, but there is a lot of combinatorial geometry behind the results I'm going to state. And sometimes you do take nice manifold models. And so deciding if two elements are conjugate here is deciding if two loops are conjugate here, except then you've got a bit more technicalities about how you give the loops and so on. But when I could talk about the complexity of the conjugacy problem, it really does correspond nicely. Now, how am I going to measure complexity? I'm going to talk about the conjugator length function. Okay, so this is these are the things I'm really going to study. So this is really the main objective study. I'm interested in these things, understanding these functions. So I'll tell you what I mean by that. Okay, so first of all, if you've got two elements or words in the group which are conjugate, define the conjugator length in U to be the shortest word or element that conjugates U to be. Okay, just take the shortest one, and then define the conjugator length function of the group. The function from the integers, so the conjugator length function at n, you just take the hardest thing there is. So you take the maximum of how big a conjugator has to be to get from U to B, well, you can either do if U and B are both less than equal to n, or you can do sum, it doesn't really matter. Have we got that? So you look at pairs of words, so that they're both length less than n, and you ask what's the shortest conjugator, and then you take the worst pair. Okay? That's the conjugator length function. Now, I said that's the group. Really, it's the presentation. Okay, but then it's just it's really not hard. Exercise is that if P and P prime are finite presentations of a group gamma, then the conjugator length function of one will be sort of the same as the conjugator length function of the other, where this sort of the same is what it always means in geometric group theory. If F is sort of the same as G, if F is sort of less than G, and G is sort of less than F, where I don't know how you all know this. Where F is sort of less than G if there exists a constant. So that F of n, so that for all n, F of n is less than or equal to, you just stick a constant everywhere you can think of. So just C of n, C Okay, so all polynomials of degree 2 are the same, all polynomials of degree 17 are the same, single exponentials are all the same. But anything with a reasonable adjective is preserved by this equivalence relation. I stick enough constants in, if not, stick some more in. Okay, so I'm interested in conjugator length functions, okay? So, do you want to say anything else? Oh yeah, so a little theorem, so a little t, is that the conjugate, so under these circumstances, where I've got my grouping from that group of compact manifolds, say, the conjugator length function of the group, what does it mean geometrically? I'd like to make some statement here about the manifold, okay? And it's the homotopy width function of maps from S1 to the manifold. Okay, so what's this thing? I won't write out the symbols, I'll just do it in pictures. So there's my manifold, right? You give me two loops in it of length. So I've got, say that one. So that's C0 and that's C1. And the length, the length of C0 and the length of C1 are both at most n. And I'm interested in the geometry of the homotopies. I'm interested in the width of a homotopy. So I'm supposing that they're freely homotopic, which I'll write like that. Everybody happy? So I can slide one to the other, right? So what does that mean? Well, it means there exists an annulus that maps, not injectively, but will map to the manifold, so that C0, so this end goes to C0 and this end goes to C1. And what's the width of the homotopy? Well, it's just this length here. Okay? That's the width of the homotopy. Okay. So you quantify over all loops of length up to n. You try and take an efficient annulus, and that will give you the homotopy length function. Everybody happy about length? So length is just the happy path from that end to that end. So when you map it down, it has length less than something, and that homotopy width function will be exactly the same, well, up to quiddly equivalence as this algebraic function. Okay? So the complexity of the conjugacy problem as measured by this function corresponds to this geometric problem of finding efficient annuli with given ends in a manifold. Okay? So that's the geometry of it. That's what I'm interested in. Now there's an intermediate type of geometry here as well. There's a combinatorial geometry which plays a role in several of his papers. And that is the geometry of annular Van Kampen diagrams. Annular Van Kampen diagrams. I was trying last night to draw nice pictures, and I was failing. So what that is really annuli, instead of mapping into the manifold, you map into this combinatorial 2 complex of the presentation. And hopefully you've all come across annular Van Kampen diagrams when studying the word problem. But what it means is that if you got your 2 words, U and V, that represent, that are given, that are conjugate. Well, if they're conjugate, then just as there's an annulus in the manifold connecting them, there'd be an annulus in mapping into this combinatorial 2 complex connecting them. And if you sort of do some sort of simplicial approximation and pull it tight, what will happen is that you'll find an annulus. So that, and it might be degenerate. I'm drawing this. Well, let me not draw it. Let me keep it honest. It could be degenerate. It could just like that. There'll be an annulus mapping in, so each of these 2 cells goes to a 2-cell complex and so on. Now, what's the connection between conjugator length and the geometry of these Van Kampen diagrams? So there'll be a base point here, from which you read U, there'll be a base point from which you read W. And what the conjugator length function is telling you about is trying to minimize the length of the path through an annular diagram connecting that base point to that base point. So conjugator length function does indeed correspond to this nice manifold geometry of the geometry of annuli and manifold.
Can I ask? I don't really understand what the width of the homotopy is. I mean, because I could reparameterize any annulus going in. So is there some sort of...
No, but I mean the length. So give this, if you approximate this by a smooth map and pull back the Riemannian structure, I mean the length.
So that's just what the distance?
It's the, if you it's really this. Yeah, so you take an annulus that maps in.
Yeah.
And then you look at take paths that go from one end of the annulus to the other in the domain, not the range.
In the image.
No, so no, in the domain you take, and then you take, but the length is measured in the image.
Yeah. So why isn't it just really the distance between those 2 curves?
Well, because Well, you see, these loops might have the same base point, for example, right? So it's
Okay.
so it's not distance. It's definitely length and not distance.
But they're free homotopy classes, so
They're free
you can just take the
homotopy.
geodesic representatives,
You could take the geodesic.
and then it would be the distance
Which distance?
between the two geodesics, right? They're just compact sets.
Yeah, but no, it's not actually. It's not distance. No, it's really not distance.
But there's really lots and lots of ways to reparameterize.
Yeah, there are
that.
lots of possible annuli, and I'm quantifying over all of them. Yeah, that's right. Yeah, roughly speaking, the number of the homotopy classes of annuli in the right deformation class correspond to the different study solutions to this. Okay. So, the geometry of these annular Van Kampen diagrams, just like the geometry of Van Kampen diagrams, playing an important role for the word problem. These play an important role for the conjugacy problem. But I'm going to state the results just for the algebraic definition. Okay, I'm interested in these functions. But I really want to emphasize the fact that it has geometric motivation. Right, and so what are our two basic obvious questions? Oh, remark. So this here, so remark. But first thing about what these functions are, that well, I guess this is a small proposition. If gamma has a solvable word problem, then gamma has a solvable conjugacy problem if and only if this function is recursive. That's almost by definition. Okay. Right. So really, but now I'm interested in how complicated it can be. So there's two basic meta questions. Question one: which functions are conjugator length functions? Conjugator length functions. Now, why is that a sensible question? Well, there's only finitely many, there's only countably many finitely presented groups, right? So up to equivalence, there can only be countably many conjugator length functions. So what are they? So a subset of this, which I like, is what is the I want to do this blackboard bold. What is the conjugator length spectrum? What is the set of numbers alpha so that n goes down to the alpha is up to equivalence to conjugator length function of the finitely presented group? It's a countable set of numbers. Well, what is that countable set of numbers? Okay, remark. It is countable. So that's the first question, which I don't know the answer to. And then second meta question, which is something to keep you and your students occupied forever. What is the conjugator length function of your favorite group? You're trying to understand some class of groups, or your favorite group, what's the conjugacy? Yeah?
What do you accept as an answer? In some ways, the definition is the answer. If you're just saying, is there a computable function or something?
Well, no, I deliberately gave this as a sub-question, right? So I think this is a question that has a sensible answer.
What do you accept as a sensible answer?
Well, so what's that set of numbers, right?
If I just give you some other cryptic description in terms of some other functions I can't compute, and I say they're two equal sets, would you consider that a good answer? Or do I need to show that the number 7 never occurs?
Simple description.
I think you have one cryptic description, somebody could go up and do some other cryptic description.
Okay, this is a meta question, right? So, it should have a satisfying answer. I'll give a theorem in a minute that just sort of illustrates what I mean by a satisfying answer. Oh, a room full of magicians, what they Okay, well, let me actually motivate. Let me tell a little bit about the word problem. And there, so the natural function to measure complexity, is this counting up or down? Okay. So suppose you want to solve the word problem, right? What's the analogous thing to the word problem? Well, let me compare conjugator length functions and this is sort of part of the historical motivation to Dehn functions. Okay, so this is the conjugacy problem, this is the word problem of finite presented groups. So let me remind you, so if you've got a word in the free group and generators, then by definition, W is equal to identity in the group if and only if there exists an equality in the free group that says the word is a product of conjugates of the defining relations. Right, where those are some of the defining relations. Now, just as conjugator length functions says, okay, we'll take the most efficient one, you can do the same for the word problem here. So the area of the word is defined to be the least A, so that there exists an equality like that. Okay, and then the Dehn function of the group, again defined in terms of presentation, but up to the usual equivalence relation independent of it, is you take the maximum of the areas of all words W of length up to n, so that enter the group. Okay, and that's the measure, that's the most obvious measure of a direct attack on the word problem if you don't know what group's being presented. Okay, and I'd ask the same meta questions, right? Which functions are Dehn functions? What's the Dehn function of your favorite group? And this happened a lot, starting from about 1990 onwards. That was really studied, and that's a good parallel to what I'm trying to do here, right? So, so in particular, what's the analog of the conjugator length function of the isoparametric spectrum? Would be the set of alpha, so that there exists a finite presented group, so that the Dehn function is entity alpha. Okay. And a lot of work went into exploring what that spectrum was, right? And so I'm looking around for the razor, but I don't have one for it. I'm going to have to try and embarrass myself. Here we go. I see. I haven't spent enough time with you. Is that too little words or too much?
Perfect.
So let me, so what I'm going to try and do today is explain our state of knowledge so far about meta question 1, which functions conjugator length functions. Except I don't have time to tell you everything, so I'm going to try and tell you some highlights. So I'm going to focus on the conjugator length spectrum, and I'll draw analogies which connects to this question about what we know for the isoperimetric function. But let me, before I do that, just have a little section on a connection, on connecting word problems and Dehn functions to the conjugacy problem, conjugacy problems, and conjugator length functions. Okay, now, the sort of prototypical little result here is if I take a free group mapping onto some group gamma, and I take the fiber product in F cross F. The fiber products are just the set of pairs x, y, and the same image, and then this proposition due to Mihailova and Miller set independently in the 1970s is that gamma has a solvable word problem. It has an unsolvable word problem. Let's say it like that. Implies that P is an unsolvable conjugacy problem. And I might say, so if we have a standard presentation of that. P is always a finite generated group. It's the group given by the diagonal elements, the diagonal generators, and the relations comma 1. So five products of finite standard group, always finite generated. So it makes sense. Okay.
Wait a minute. You define this thing only for finitely presented groups, and P may not be finitely presented.
Oh no, sorry. Yeah, I'm going to concentrate on finitely presented, but you can. The definition didn't use the presentation. Yeah, you're right. Thank you. Okay. Now you might think, okay. So taking fiber products is a way of translating word problems into conjugacy problems, and that's sort of true. So you might think I'm really wasting my time with meta question 1 because I should just take fiber products and I'll get a correspondence between word problems and conjugacy problems, and maybe I'll get a correspondence between Dehn functions and conjugator length functions. And there is something to that, and I tried it, but it's this arrow only goes one way, right? And so if you're going to make some correspondence, better go both ways. But the if and only if theorem isn't quite what you want. So here's an if and only if theorem. So if H1 and H2 are torsion-free hyperbolic groups, so for example, 3 groups, and P, which you should think of as a fiber product, you can also say that it's a subdirect product. Subdirect products. Remember, that just means it's a subgroup of the direct product that maps onto each factor. Now, when you've got a subdirect product with only 2 factors, it's actually a fiber product. So it would be the fiber product or something. So it would be a pair of maps. I want you. There's some nice exercise you've never done. It's every subdirect product is a fiber product. So then you'd like to say something about the conjugacy problem in P versus the word problem in Q. Okay? And there is an if and only if theorem, so that's P. Then P has a solvable conjugacy problem if and only if. Now, you might be hoping I'm about to write, so I will. Q has a solvable word problem. Now the trouble is the next bit. And there exists a uniform algorithm to decide membership of cyclic subgroups. Yeah, that's sometimes called the power problem. What I really mean is you give me two words in the generators, U and V, and you have to tell me if U lies in the cyclic subgroup generated by V. Now that
Uniform here means what?
Yeah, sorry, let me say that. There exists an algorithm that, so that given U and V, those are words in the generators, decides if U is in the cyclic subgroup generated by V or not.
No.
Yeah, I mean that. Yeah. Now, this is a surprisingly subtle problem. There exist groups in which you can decide that problem without being able to decide whether an element has infinite order or not. It's really it's a more subtle problem than it first appears. And in particular, since this is an if and only if theorem, you're not just going to be able to translate the complexity of word problems into the complexity of conjugacy problems by taking power products. At least not naively. But you can do something. So you're going to have to control the geometry of cyclic subgroups as well. Okay. Now, and getting that control is going to cost you something. It won't be arbitrary groups, but nevertheless, you can prove the following: that if something is a Dehn function of a finite presenter group. Now, I'm going to put a little asterisk there and then explain why there's a little caveat. Then there's this finite presenter group, P, because it will be a private product, so that its conjugator length function. So I'd like to say that conjugator length functions are kind of the same as Dehn functions, because as I'll say in a minute, we understand Dehn functions. But in fact, it's less than n squared times the Dehn function evaluated at n squared, which isn't so bad, right? It turns polynomials into polynomials. Doesn't turn single exponentials into single exponentials, unfortunately. So it's not as the connection between the group that has that Dehn function and the group that has this conjugator length function is not as direct as over here. But nevertheless, you give me a Dehn function, I can cook up a finite presenter group whose conjugator length function is similar. So the fact that we understand the wide diversity of behavior among Dehn functions means you'll get a similarly diverse range of behavior among conjugator length functions. Now, what's that little caveat up there? This is something that's irritated me for years. The Dehn function has to be standard, i.e., there exists a group of type F3 with Dehn function. Now, so groups of type F2, if it's finitely presented. Type F3 means there's a classifying space for the group with only finitely many 3 cells. It's every Dehn function ever constructed is standard. It's not clear if every Dehn function is standard, but every Dehn function that's known is the Dehn function of a group of type F3, and that's probably a theorem, but I don't know how to prove it. Okay, but the point of that theorem is not so much the sharp bounds, it's just to say that we expect conjugator length functions to be at least as diverse as Dehn functions.
In theorem 1, though, Q is not just any group.
Yes, it is. It's only a finite presenter group. Sorry. It can be any finally presented group. Yeah, because I could just take a free group mapping onto this, but then I wouldn't be able to make the fiber product finally presented if it's a free group. But I can. Yeah, you can take Q to be arbitrary and do a reverse construction. Okay. As ever, the introduction took longer than anticipated. Let me start telling you some nice examples of conjugating length functions. Any questions, Juan?
So in this theorem, can you draw this condition and try to just get a finitely generated group with this kind of conjugator length function?
Yeah, thank you. Yeah, the thing about being standard is part of you needed to plug into the machinery to make the group finally presented. Yeah. So, yeah, if you're happy just with finally generated, you wouldn't. I suspect, I haven't tried hard, you know, because I suspect it's much easier. If you don't want to make groups finally presented, it's much easier to make them have conjugator length functions you want them to have. So there's probably it's much easier. So you can certainly do better than those bands up there. Not perfect. Right, so let me now compare I'll just stick to small functions, so I'm going to compare the isotenometric spectrum to the conjugacy length spectrum. Okay, so remember this is the set of alpha, so that n to the alpha is the Dehn function. This is the set of alpha, so that n to the alpha is the conjugator length function. Right. What do we know over here? So we know that if the conjugator length function, you can get lots of them that are n, and that's if and only if the group is hyperbolic. Here, well, there just exists lots of interesting groups and gamma, so that the conjugator length function is linear. Lots and lots and lots of them. Right? So lots of geometric examples, lots of the hyperbolic groups certainly, but lots of other things too. Right? So I don't have any notion of of a reasonable theorem like this saying that that there's something interesting you can say about all groups that have a conjugator length function that are linear. I think it's just too big a class. It's not enough of a restriction, I think. And then there's a famous theorem of Gromov's gap theorem, right? That if between 1 and 2, you get no groups. You know, if the Dehn function group is less than quadratic, then it's linear. Now that, I think, is an interesting question, and I don't know the answer to that. Okay? I don't know if you can cook up a finally presented group whose conjugator length functions n to the, try and pick a number between 3 over 2. It'll take a little while, but if you give me an integer, then you can come up with a group whose Dehn function is polynomial of that degree. And let me give an example. These weren't the first examples, but they're all early examples, and they're the model filiform groups. Okay, so those are semi-direct products like that. And what's the action? The action is these have very interesting geometry that's been studied from lots of directions. Classic Carnell groups in geometry. So the action just you've got a basis and it shoves them all along until it gets to the end. And then it fixes one. Okay? And that, the Dehn function of that group, is polynomial degree d plus 1. Okay. In fact, there'll be a theorem that goes here in a minute. Okay, well, I'll just tell you. Now, I'm going to tell you 2 theorems there. Am I supposed to be stating these as I go along? No, but let me mention one other thing that goes here, that if gamma is nilpotent of class C, then its Dehn function is polynomial of degree at most C plus 1. You can bound the Dehn function in terms of the nilpotency class. And then finally I want to mention the closure of the isoperimetric spectrum. So you get 1, then you get this gap, and then there are no more gaps. The exponents are dense from 2 to infinity. Okay? That's something that myself and Noel Brady proved in the 90s. And then there's a much better theorem with Piaget, Rips, and Spear, which I'm not going to write down, but I'll say what it says. It says that we do know what these numbers alpha that appear as exponents of Dehn functions are, more or less, after the P versus NP problem. And they're all numbers, all computable numbers, where the decimal expansion can be computed reasonably quickly, with a technical definition of what reasonably quickly means. That's the sort of answer we're looking for. And it might be that this is the same set of numbers, but I don't know. Okay? So what do we know? Let me start writing some theorems. So these theorems are all Tim Riley. Okay, so how many theorems do we have so far? 2. Okay, theorem 3, that's myself and Riley. I gave these examples for a specific reason, and there's the conjugator length functions, so those same model filiform groups, that same potent group, class D plus 1 and class D plus 1, that has conjugator length function that's polynomial of degree something. D. Okay. Now, that looks like it's just a translation of this. It's not. It's really a separate theorem. And to emphasize that it's a separate theorem, I'm hoping to have a bit of time to talk about these proofs. It's probably a vain hope. I'll try and say something about the proof. But let me... all these theorems that I say now are with Riley. Let me say it's not just a general, the upper bound is not just a general thing about nilpotency class anymore. How shall I say this? I thought about it saying in my notes. Okay, let me say like this. So talk about two-step nilpotent groups. Okay. So what's a typical two-step nilpotent group look like? So you've got your center, and I'm going to assume that the center has this generated being group, and assume it's virtually z to the n. Okay, so it's got rank m, rationally. Okay, there's my nilpotent group, and then there's the being group. Okay, so it's just two-step nilpotent group. For all of those things, there is a bound on the conjugator length function, but it's not. See, the Dehn function of such a thing is always at most cubic. But the conjugator length function depends on this rank here, and it's at most degree n plus 1. Okay? Now, you might think that's just Bridson.
Well, you have two different n's, I think.
What's my other
Or isn't m? Yeah, okay, m. That's
Okay, let me make that a D. Yes. You might think, oh, it's just Bridson being pathetic, right? It probably, if you tried harder, you'd make a uniform band. But no, there exist examples, okay? So there exist groups where that's as really as Zm. So for all m, there exists a group, we'll call it Gm, basically an m plus 2 here. I'll write the m plus 2 like that for a reason, because I'm going to describe these groups to you. So here I'm going to have some central generators, and I'm going to have some generators of that guy, and I'm going to have two generators of that guy. There exists that show this is sharp. Okay, so the conjugator length function of these groups really is
Yeah.
polynomial of degree. I don't know if it's supposed to be. It's d plus thank
Yeah, it's okay.
That's d plus 1. Okay. So even among nilpotent groups of class 2, you get arbitrary polynomial behavior. I'll write a presentation what that is. This is in a paper that has the words systems of linear Diophantine equations. I'm not going to get solve the proof. What this comes down to is understanding the size of solutions to systems of linear Diophantine equations. That's what it comes down to. You use normal forms in nilpotent groups, and you think about shuffling the normal forms. You compare exponents. You get systems of linear Diophantine equations, and you're interested in the size of solutions to linear Diophantine equations. And you rig up these groups to make things bad. And so what are these groups? So you have these central generators. You have DAs, then you have two Bs, B1 and B2. And the CI is central. And you have everything that says that B1, B2, so am I forgetting anything? No, that's so I have these relations crucially, okay? So the sequence splits over that. But what doesn't split is when you conjugate B1 by AI, it doesn't commute, it spits out a CI. And when you conjugate B2 by AI, it doesn't commute, it spits out a CI inverse. That's, it doesn't look very violent, but that will do. That group, the conjugator length function of that group, really is polynomial. And as I prove it by analysing the system of linear Diophantine equations you get. So these are two different proofs that you get arbitrary polynomials as conjugator length functions. This is algebraic and a bit of arithmetic. This is much more geometric. This is related to the Cornell geometry of these groups. It's a proof by induction, and I'd like to say something about it, but I'd rather say something first about another theorem. Okay? And the other theorem is this thing that you'd like to get a dense set of exponents in at least some range. So the next theorem I want to talk about is that the conjugator length function closure at least contains a dense set of exponents between 2 and infinity. And in order to make sense of that, well, there's a theorem, but somehow the interesting thing, and this is the hardest theorem I want to talk about today, the interesting thing is how you get these exponents, because it's a sort of geometry that I keep returning to because I love it. Snowflake geometry, snowflake groups, which are groups that Noel Brady and I invented to prove this theorem up there about the isoparametric spectrum. And one of the beguiling things about this class of groups is just how easy they are to describe. And then they have this really lovely geometry. By the way, while I'm cleaning this, I might say that a variation of what I'm about to describe was developed by myself and Brady and Shankar and Max Forrester to prove to give explicit groups, two-dimensional groups, so that you give me any rational number, you can cook up a group, an explicit group whose Dehn function is n to the alpha, with alpha your favorite rational, bigger than 1. I don't know how to do that. Bigger than 2, thank you. I don't know how to do that for conjugator length functions yet. I don't know if you can get every rational number as an alpha in the conjugacy length spectrum. But let me, oh no, who knows. Let me describe the snowflake groups. I don't think I've got about 10 minutes. Yeah. Okay, so this is myself and Brady in the 90s. And we invented them explicitly to solve this problem. And they really are very easy groups. So you take a torus, okay, so that's just a, it's called T, so that's A and B commute. And then you stick 2 cylinders onto that. And so I'm building a space whose fundamental groups can be the group I want. So let's say the first stable letter here is S. So S, oh, and I fixed 2 integers. P bigger than Q. Positive integers. And the first stable letter conjugates A to the Q to A to the P times B. So it's going to be a relation like, oh, I just rubbed it off. It's like the presentation I just had there, that you do a B and a B inverse. And so the second cylinder, you stick 2 cylinders on, both stuck onto the torus. The second cylinder, also one end is attached, wraps Q times around A, and the other time wraps P times around P, but instead of doing B, it does B inverse. Okay. So that's the group. So it's got 4 generators, 1, 2, 3 relations. That's the PQ group, snowflake group. And the theorem that Brady and I proved is that this group has an interesting Dehn function. Its Dehn function is n to the 2 alpha, where alpha is log to the base 2 of 2p over q. So unless that's an integer, that's a transcendental number, right? So here's an infinite family of groups whose Dehn functions have transcendental exponent. And as you vary p and q, that gives you a dense set of exponents between 2 and infinity. Okay. Now, I thought a few months ago that I was going to tell you that the conjugator length function of this group is something similar. It's also something transcendental. And it's not, much to my surprise. So this is the conjugator length function of this group is linear. Oh dear. It's not obviously linear, but it's linear. Okay? Now, okay, but I want to use the I'll draw a picture in a minute to show why this is called snowflake geometry, where these transcendental exponents come from. So the next thing to try is to exploit the geometry of these cyclic subgroups generated by A and B. And I'll explain to you what I mean about that geometry in a minute. So I take the same group, I take an H and an extension of it, I'm going to add another cylinder. But this is going to do something quite boring. Both ends are just going to be attached to B. So I have the same relations as before, except I've got this new relation that I've just added a new stable letter that commutes with B. Okay, now I had a reason for that, but that didn't work either. That better have a name. It's got a plus, okay? BPQ plus, its conjugator length function also sadly comes out to be linear in a slightly less obvious way, but in the end it collapses. Okay, now I was doing something with central extensions over there, and if I had longer, I would give you a lecture about why central extensions are very interesting in terms of conjugacy problem. And you want to control them in a certain way that's really quite subtle, and this is where a lot of the beauty of the subject lies. But now I'm going to take a central extension of this group. Okay, so I'll use the same letters, but I'm going to change the relations, and I'm going to have a new central generator. And I'll keep the old relations, except I changed just this one. Okay, except I changed that one just to be Z. Okay, take that central extension. And the conjugator length function of that one, after much struggle, is n to the alpha plus 1. Good. Where alpha is log base 2. Okay, so it's not, over here, the Dehn function, it was 2 to the alpha. Right? Here it's alpha plus 1. But nevertheless, you can manage to encode this fractal geometry into the conjugator length function. Now, that's quite hard. Okay, that takes a long time. Well, the current proof is really quite long and quite hard. But I want to explain, I want to demystify a bit in the remaining 2 or 3 minutes. Is that right? Oh no.
Yeah, it is right.
Do I? Oh, I started early, right? Yeah. Okay. Yeah. Okay. I want to demystify a bit where this fractal geometry comes from. This is where I need my code short. And the key to there's 2 propositions here that matter. Is that the second one, which I'll say, the geometry of the central extension matters. So in this central extension down there, the distance in the ambient group along the center is distorted like that. No, sorry. It's distorted like that. I can't remember whether it's alpha or alpha plus 1 is down there. It's distorted like that. Okay? So that center is deliberately, that group is constructed so that this center is really distorted. That center of that group is really distorted. But the harder proposition is this one, is that in the original snowflake group, there exists a constant so that for all elements of the torus, all the elements over here, so this is the subgroup generated by A and B, you can say very precisely how that's distorted. Now, often, when you're doing arguments with distortions, many of you know, you can get one-sided bounds, or two-sided bounds with different constants. Here you get a very precise distortion, that it's 1 over kappa. So I take this disk, I don't know which side of I put the constant on. If I take the distance in the torus, I want to compare that to the distance in the ambient group, and then I want to bound on the other side, which is the distance from the torus again. Kappa, 1 over kappa, and then I want to put an alpha somewhere, and I put it there, so 1 over alpha. Okay, so you get a very precise bi-Lipschitz bound on the distortion of the center. So let me draw you a picture. And so then when you start trying to solve conjugacy equations, things that would otherwise be linear get distorted in this power alpha way. Okay, and that is morally what's going on here. That's what you're trying to encode into these groups, is that you take a group where the conjugacy function is linear, and by taking a central extension where you control the geometry of the center, you can distort distances by this alpha power, and therefore get these weird conjugator length functions.
So do you have a general result that if you have a group where the conjugator length function is linear and you have a central extension where the central is totally distorted, then you have control over the...
That's a good... No, it's more subtle than that. And it goes... You really need to understand the structure of centralizers in the group modulo at center. And it really depends on those. There's some things you could say in general, but they would be very weak. But what you really need to understand is centralizers. You see, things go wildly wrong if you don't control centralizers. So let me remind you, these amazing finally presented groups of Collins and Miller. So the group has a solvable conjugacy problem, but it has a subgroup of index 2 that has an unsolvable conjugacy problem. Now that just shows you things are really very delicate, right? And what goes wrong there is centralizers go to hell when you pass the subgroup of finite index. And so and it also tells you, right, that the conjugacy problem is not a coarse invariant, that it changes wildly with Clothier isometry. So it's not, it can't, somehow statements just about the geometry of the center will be very weak for that reason. Okay, so where's this fractal behavior coming from? Well, look at that group, right? So P is bigger than Q. So suppose you want to go along A to the Q in an efficient way in this group. Well, what would you do? Well, you would go, you go along S, and then you would go along the other side, because that's suppose that's A to the Q to some big power. And that's A to the P to the B to some big power. You just made a shortcut. Okay.
Actually, you're assuming P is larger.
P is larger. Oh, damn. Right, thank you. Yeah, that's good. I got my picture upside down. Yeah. Let's try that again. A to the P to some big power. Then I would adjust it. Right, so that you want to go from there to there, right? So I'm going from there to there. You would adjust it by adding on some B's. And then you go across that strip to get to A to the Q to the end. Right, so what did I adjust it by? I adjusted it by something you should think is small. Yeah, I'll come back to that. You mean.
And now the B is missing.
Yeah, so let me make that A to P to the B, just to make the point, right? And then there's no epsilon. I go across, I get to A to the Q. But now, I could write that as some big power with B's, yeah, 2. Oh dear, I shouldn't. Right, that's right. Okay, the B's cancel out, and I got the A's, right? But now I could do that again, can't I? I can go across the strip to make that much shorter. And now there'll be a little bit of error, because I can't really always take n over 2, it might be odd. But I can keep doing this, right? And then that's not short yet, because if it's still quite long, then I can shorten it by going across another stable lattice strip to make it shorter. And I'll keep doing this. And as I go out in the layers, crudely speaking, I'll be shrinking the length of these strips by a factor of Q over P. I'll keep going until I've got nothing left. How many layers will there be? Will there be some log? Right? And what will be left at the end will be something I'll be able to estimate. And so instead of that being the geodesic in the geodesic in the group does something like this, and it's logarithmic. Right, and that's obviously why they're called snowflake groups. You can see it's not a complicated idea as to where the distortion comes from, but getting the precise estimates is a bit delicate. So that picture explains why these transcendental exponents alpha come in, and then there's some work to turn them into conjugator length functions. So that's where we're up to with small conjugator length functions. We can also do stuff with bigger conjugator length functions, but the main point is just there's still a lot to do. Thank you.